I wanted to work through a problem of calculating the energy stored, electrical energy stored in a collection, an arrangement of charges. In this particular problem, we've got three charges. They're each positive 2 microcoulombs, so they're all charges of the same sign, same size. These three charges are arranged at the three corners of an equilateral triangle, and the sides of the equilateral triangle are 1 centimeter on each side. That's what equilateral means. So I pictured the arrangement of charge over here on the left-hand side. I just drew this drawing. Here are my three charges. I call them Q1, Q2, Q3. Here are the three separations of the three pairs of charges which form the sides of the triangle. And we've got to calculate the energy of this arrangement. A similar problem to this arrangement of three charges, and what's the stored electrical energy of the arrangement of three charges. A similar, simpler problem is the arrangement of two charges, and what's the energy stored by an arrangement of two charges. So in that problem, here are our two charges. The procedure one could use to solve the problem is to imagine starting with the charges far away from the whiteboard and bringing up the first charge and asking the question, how much work do I do? What is the energy cost to me in bringing up the first charge? And then bringing up the second charge, asking the question, how much work do I do? What is the energy cost to me of bringing up the second charge? And then the total energy cost, the total amount of energy stored, will be the sum of the two amounts of work that I had to do in bringing up the two charges. When you do that calculation, when you first bring up the first charge, because the potential is not changed for the first charge, there's no cost in energy, there's no work done. When you bring up the second charge, now we're bringing the second charge into the region of potential of the first charge, there is work done, there is an energy cost. And so the total amount of work done is 0 for the first charge, non-zero for the second charge, and that tells us the stored energy. What you discover is that the amount of energy stored by this pair of charges is given by a formula. It's given by an equation after adding up these two amounts of work that are done. It's given by a formula, given by an equation that is simply K, the Coulomb constant, multiplied by the product of the two charges, Q1, Q2, divided by the separation of the two charges, R. It's that simple. That's the resulting stored energy of this arrangement of two charges. You would find that whether you brought up the charge on the left first and then the charge on the right, or you did the reverse. You brought up the charge on the right and then the charge on the left. It's always K times Q1 times Q2 divided by R. And so that's another way, once you know that a pair of charges stores K, Q1, Q2 over R. It's another way of calculating the stored energy. It's a very useful way because you can extend that. You can extend that easily to more than two charges, to 3 charges, to 4 charges, to 5 charges, and so on. Our particular problem here involves 3 charges. It's easy to extend that idea that a pair of charges stores energy K, Q1, Q2 over R to 3 charges. The way you do it is if I have 3 charges in an arrangement, I've got 3 charges, the red one's the extra one. Those 3 charges consist of 3 pairs of charges. There's the 2 blue ones. There's the top blue one and the red one. There's the bottom blue one and the red one. So there's 3 pairs of charges here. If we add up the energy of each of those 3 pairs, so K, Q1, Q2 over R, plus K, Q1, Q3 over R, plus K, Q1, Q2, Q3 over R. If you add up those 3 contributions from the 3 pairs to the to the energy, you get the total electrical energy of the complete arrangement of three charges. And so that's what we're going to do. We're going to use that way in this case of calculating the energy of the triangle of charges. We're going to figure out the energy of the triangle of three charges by figuring out the three energies of the three pairs of charges and then just adding them together. You could extend this to four charges. If you had four charges, there'd be many more pairs of charges. But if you just evaluate with K, Q1, Q2 divided by R, use that equation for each of the particular pairs of charges and then add up all those energies from all of those pairs, you get the total energy of four pairs of four charges. Okay, so let's go ahead and implement this idea. The basic idea is that the potential energy of the entire arrangement of three charges is the sum of the potential energies of the various pairs of charges. So just to be clear, there's one pair here, it's Q1 and Q2. There's one pair here, it's Q1 and Q3, and then there's a final pair here, which is Q2 and Q3. We've got to add up the energy associated with each of those three pairs. I'm going to label them as potential energy 1, 2 between charges 1 and 2. Potential energy 1, 3 between charge 1 and charge 3, and potential energy, what's the remaining one? It's 2, 3 between charges 2 and 3. We just got to evaluate those three contributions. So, for example, for potential energy 1, 2, we said the rule is for a pair of charges, and there are three pairs that we're going to work out here. The potential energy of the pair of charges is K, the Coulomb constant, times the product of the charges, this will be Q1, Q2, divided by the separation between the charges. Maybe to be clear, I'll call that R12, because it could be different. It's not in this case, but it could be in general. We just got to fill in all these numbers now to get this contribution to the potential energy of the arrangement of charges. I'll just put in the numbers. I won't put in the units just to save some time here. I've got 9 times 10 to the 9 Newton meters squared per Coulomb squared, Coulomb constant. I got 2 times 10 to the minus 6 microcoulombs. I got another 2 times 10 to the minus 6 microcoulombs. And then in the denominator, I've got the separation between the charges is 0.01 meters. It's 1 centimeter. If I multiply and divide these numbers up, I get, well, look at the powers of 10. This is interesting. I've got 10 to the 9 in the numerator. I've got 2 10 to the minus 6s in the numerator. So combined, that's 10 to the minus 3 in the numerator. But I'm dividing by 10 to the minus 2 in the denominator. So actually, the powers of 10 just lead to 10 to the minus 1, 0.1. It's 0.1 times 9 times 2 times 2. 9 times 2 times 2 is 36, times 0.1 is 3.6. 3.6 joules. So that's the potential energy of the first pair. Now, in general, if we got three charges, we then go on and calculate the potential energy of the two other pairs. One of them would be P13. We'd calculate that. The next one would be P23. But in this particular case, the separation between the charges in each pair is always 1 centimeter. The values of the charges is always 2 microcoulombs. And so these three potential energies of these three pairs is actually always the same, and it's just that 3.6 joules. And so in this particular problem, all I've got to add up is these three contributions from these three pairs, each 3.6 joules, to get the total energy. I'm going to actually just write it up here. That total energy will be 3.6 plus 3.6 plus 3.6, and that comes out to be 10.8 joules. And that's the total energy that's stored in this arrangement of three positive charges. It's positive. That means simply that we had to do some work to push those charges together, it means that those charges, well, they're all repelling one another. They want to fly apart. If they flew apart, they would release that 10.8 joules into their kinetic energy as they kind of blew up. And so we've been able to solve this particular problem of the energy stored by three charges in a really rather simple and straightforward way, based on a result from our earlier work with two charges. We figured from actually doing the task of assembling pairs of charges that the energy stored by a pair of charges is K Q1, Q2 over R1, over R12. And then we use that as a kind of building block, for thinking about the energy of this arrangement of three charges that has three pairs. And as I say, you could do this for 4 charges, you could do it for 5 charges. You can see probably how for 3, 4, 5 charges, it's a lot easier to solve the problem this way by thinking of how many pairs of charges there are than to solve it by one, bringing up the charges into the electrical potential of the other charges. That gets very, very laborsome.